Okay guys, last time we were finishing up with foliation, and this is really how the minerals inside of a rock will align in the rock due to the compression or the stress related to them. So a great example is up here in the header, right? These rocks, you can see the banding of these rocks is occurring. It's kind of like taffy in a sense, where you're pushing on it, and then they start getting all these little like these folds and things inside the system, right? So for example, in this book here, if I actually start pushing on it, it's going to actually start to bend, right? Okay, and that's a type of foliation over time, as it starts to align itself within the rock. Okay, and so so here's some examples of all these different foliated rocks, with all the way from low grade all the way up to high grade. So here's a slate, and these ones are sometimes hard to tell if it's actually foliated or not. You can kind of see right there at the edge there. You can kind of see some of these foliations here, but that often is some of the past bedding of the shell as well, right? Okay, but that's really often how the foliation works. If you have these beds of material coming over time, and then you have put weight on top of them, well, they're going to smash down in the same direction of the beds. And so that would be still an example of foliation. Now, if you go here, you can still see the foliation wells here. You can see the lines start to come through here. As you start pushing more and more onto the rock, it will start to, different minerals will start popping out as the fluids or the grains actually change, right? And so here's an example of phyllite, which is your low to medium grade metamorphism. And then you start getting into your schist here. You can see these little dots here. These are garnets that are starting to form. And you can see how all of the platy minerals are actually all oriented in one direction. So that means the pressure was coming from the sides here on this rock. But you can see the direction of the foliation. And the last one here is this gneiss, which is the bands that you see here, where you're pushing on it so much that you start getting into these banded, these bands as they orient themselves in the same direction. Okay, so slate all the way to gneiss. Now this could all have the same exact protolith or parent rock, and it could over time go through this whole process from slate to gneiss. Okay, so here's some examples here where you go from slate, phyllite, schist, gneiss, and we can even go even higher grade to migmatite, but we're not going to go there today. We're going to be focusing on just these lower four here. Now, as you increase in metamorphism, what will happen is you have increased grain size, so the actual crystals inside the rock become larger as you go from low grade to high grade. Okay, because that's that recrystallization. And then the foliation actually gets larger as well, or you get this increased coarseness or banding kind of pattern to it as you continue on and get it bigger and bigger. So you get your slate, phyllite, schist, and then your banding in the gneiss. Okay. So here's some examples of some other protoliths. Here's a granite. So this would be a granitic gneiss. So it came from the granite, went to the gneiss because of the chemistry over time. Well, this is a basaltic gneiss. Now notice the difference here. There's different initial chemical composition. Thank you. Okay, so it actually looks a little bit different, but the texture is the same. And so we both call them gneiss, but this is a basaltic gneiss, whereas this is a granitic gneiss. Okay, then you can do the same thing with schist or anything like that. You can have granitic schists or basaltic schists or anything like that. As long as it has that texture, it's still a schist or a gneiss, depending upon if it has the bands, right? Now here's an example of a conglomerate rock, a sedimentary rock. Now if I squeeze this one, it would have foliations too, but now what's happening is these individual grains are getting elongated as it's getting compressed to form into what we call metaconglomerate. Okay, so this is a great example of these rocks that have different protoliths over time. They can be both gneisses, but different over time because of their chemical composition. Okay, however, there are also rocks that we have that we call non-foliated rocks. These non-foliated rocks do not show that preferred orientation, and this often is because of the actual composition of the mineral itself. it can flow a little easier, and so it doesn't actually, when it recrystallizes, it doesn't go in a preferred direction like some of these platy minerals do, and so therefore you don't see these patterns in them. However, be careful with some of these sometimes, because like for example in this one, this is a marble, and this is the old impurities that were inside the limestone, had some dark impurities and some lighter impurities, and because of that you can kind of see what some people think are foliations, but they're not. They're basically remnants of old bedding. So you got to be careful with that. Okay, but marble is a great example. When it goes from limestone to marble, much denser. Limestone it has a lot of, still has some air spaces in them, and the bonding is not as strong. But as soon as you actually compress it over time, it's much more dense. This is why people who do sculptures like Michelangelo doing the David and things like that are using marble because of how dense it is. If they did limestone, it would actually break off into pieces, and it wouldn't actually have these nice smooth surfaces, and also couldn't actually carve it as well. But because you have marble, you can do a much better carving of it, and you can form statues and other things from that marble. We use marble a lot in other things too, as you probably already know. We use it a lot in building supplies. So some of you guys might have marble countertops at home. Hopefully not in your kitchen, because marble countertops tend with acids tend to dissolve away. Remember we talked about hydrochloric acid and put it on a limestone and it will effervesce. Okay, basically it's just dissolving it. So if you have a marble countertop and you start putting acids on it, like tomato juice or things like that, it doesn't do very well in a kitchen environment. Now, it can do well in maybe a bathroom or something like that, where you don't have those acids on a regular basis, but they don't do as well on that. So here's another great example where we use a lot of marble. Here's what this is the Lincoln Monument. Memorial in Washington, D.C. There's tons of marble throughout this. They actually, if I remember right, got marble from like 15 different states just for this monument. They did that on purpose to actually have different representations of the states all around the nation. It's kind of cool. Okay, but anyway, so that's an example of a non-foliated rock. Another example of a non-foliated rock is quartzite. Now the protolith for these is really that quartz sandstone. And so remember, in quartz beaches and sand dunes, a lot of the other minerals basically get weathered away, and so all you have left is quartz. Now, if you have quartz and it acts a lot like calcite in a way, where it won't go into those preferred directions again. However, it still can start getting that bedding, that old bedding. So be careful with those. But most of the time, it will be this doesn't have a preferred orientation associated with it. Okay, a metamorphic orientation. Okay. So that's what we call different types of foliation and the high grade versus low grade metamorphism and foliation. Sorry. Okay. Now, how does this all relate to plate tectonics? We've kind of already talked about this, right? Okay, so in places where we have water flowing through, you could have low pressure and relatively low temperatures, and therefore you can get low-grade metamorphism at a divergent plane boundary. So a great example of where you can get to this, you can at a divergent plane boundary, you're going to have some heat, hardly any pressure, which means that you can actually have some changing of some minerals. Okay, and these are what we call different metamorphic facies, or different grades of these minerals. And I'm not going to ask you to know the different facies of high grade to low grade kind of facies, but the point comes here is that high grade material will actually be further down usually, and the lower grade material is further up because of the different pressures associated with them. Now, where metamorphic rocks is really the most prevalent really is in convergent plane boundaries. In both oceanic, basically in any actually convergence, oceanic convergence, ocean-ocean convergence, or ocean-continental convergence, or continental-continental. Any of those can actually have metamorphic processes occurring. Now, remember, at a continental-continental, you don't have any volcanics associated with that, so you don't have as much heat as you would if you have a subduction zone, because you have both contact metamorphism and the pressure associated with it as well. So you can get some really low grade metamorphism towards the top, medium down below, and then higher in places of higher friction and stress, right? So just realize that metamorphism and plate tectonics go hand in hand. And so, but mostly that old metamorphic rocks are in these cores of these old mountains, right? So here's an example of how the rock cycle actually changes in context of plate tectonics. Okay, so for example, I might have I'm just going to go through this. At the beginning of this example, atoms rise to the surface via the mantle plume, and to form volcano on the surface. That volcanic rock erodes into sediment. That sediment accumulates on the coast and maybe some beaches. Okay, and slowly over time, you might have clay off the shore to produce shale, all from that volcanic origin. So we start with a volcanic nature, goes into a solid form, to a sedimentary rock, erodes away, deposited, and forms into shale. Okay, when the continents collide, the shale ends up being buried beneath the mountain, where you have nice hot temperatures and high pressures, and therefore can be metamorphosed into slate, and then eventually into a schist, right? Now, eventually, the mountain range might erode away, and you'll start having the material down below get, because of isostatic rebound, will start being exhumed, and so we'll slowly come to the surface to actually expose that schist on the surface, just like the Piedmont here in North Carolina, where that material has actually been now exposed on the surface. When it really went through the same process that we're talking about right here. Okay, because we have schists and gneisses all over the place in North Carolina. Now, eventually, over time, you might actually have a divergent continental divergence or a plume come up through here and start pulling this away again, and then you can start getting that schist to melt, to go back into a magma that can then be reincorporated into an igneous rock somewhere else, right? So here's one example of how the sedimentary cycle or the rock cycle goes through the whole process to form metamorphic rocks, igneous rocks, and sedimentary rocks all in one whole process. Okay, and these plate tectonic settings can actually help you with this. By the way, clue for you. This isn't a great example of some stuff that you do in your discussions this week. I ask you to do things like this to help tie these ideas together. Okay, and that's really what plate tectonics is this unifying theory. We talked about it a little bit last time, but it helps us to get that unifying theory coming together. Okay, so now we're going to do some quick review. Like I said, these lectures are a little bit faster. Is this foliated? How did it form? Well, absolutely, this is foliated. You can tell from here. These rocks that probably was a conglomerate at one point have now been basically compressed, and they've been compressed from this direction, right? So here's the pressure, and then the oriented preferred foliation is in this direction, back and forth. Okay. Now the next one here, is it foliated or how did it form? Well, if I actually have this going as a slide, let's do it real quick. There it goes. Here is that parent rock, and this parent rock might have been a medium-grained clastic sandstone, right? Okay, so and by compressing it, or maybe adding some heat to it, it might have come from a beach at some point. It could actually be formed into what we call quartzite. Now remember, quartzite doesn't like to be foliated. You can't really see much any foliations in here anyways. It looks just like a massive thing of quartz. So this would be what we consider a quartzite, a non-foliated quartzite, and usually caused by low-grade metamorphism. Okay? So here's the parent rock. Here's the parent rock, which is clay, maybe a shale, right? That muds off the coast of maybe a beach somewhere, or off the coast of the continent. And then this is the metamorphic rock. So here's the protolith, or the parent rock, and here's this. And now this one you can see, this is very fine-grained foliation. It's hard to see here, but this is a foliated rock, and this would be shale and slate in a sense of the metamorphic rock. Okay, here's that same shell that could then also be a schist, would be a medium grade metamorphism. Okay, and then you can get that same thing to turn into a gneiss, like this one here would be the high grade metamorphism.